Hello, my dear students, and welcome back to our continuing discussion of Chapter 2. It's a rather eclectic chapter titled Atoms, Molecules, and Ions, and covers quite a broad range of topics in chemistry. We will cover them superficially, and the important concepts that I don't feel are covered in sufficient depth, we will cover again as we meet those topics or need that background as we go through the course. So let's finish chapter 2. We finished talking about the Dalton's atomic theory and Rutherford's modern nuclear view of the atom, which brings us to our discussion of the elements and a little bit of the periodic table and some important concepts about the elements. So let's get into it. Now, when you look at a periodic table, you will see all these letters up there, and those letters are called symbols. They're not abbreviations. For one thing, we have 118 elements and only 28 letters in the alphabet. So obviously, those are not abbreviations. They're symbols. And they really are symbols. For example, some of them derived from symbols that Dalton used and alchemists used long ago. For example, Dalton had hydrogen for number 1 and helium for number 2. And he had a bunch of different true symbols for his elements. I don't even know. I can remember what some of them looked like, but I don't know what they all were. I suspect that the one that was a little Z inside it was a zinc, and he had one with an S inside it, I think was sulfur, and one with a P inside it. That was phosphorus. But now we have a symbol, a 1 or 2 letter symbol for each. And then we also have the atomic number. And that is the number 1 through 118 that you see, usually the big letter, usually in the top left or even in the middle of the box for each element in the periodic table. And we write it formally down here at number 6. And then up above we have, which we sometimes write, a mass number, which is the number of protons plus neutrons. That mass number for any given atom, not any given element, I'm going to qualify that in a minute, for any given atom is the sum of the protons and the neutrons. Remember we said for our purposes they are both equal to 1. There is a slight, out in the 4th and 5th place, difference between a proton and a neutron in its mass, but for our purposes they weigh the same. And for our purposes, an electron, which weighs, takes about 1,840 of them, depending on what book you read and how old and how new it is. I learned 1,780 electrons per proton. But those electrons don't add up to much. Even in the heaviest element at 118, they equal a small fraction of a single proton. And of course, that element 118 has 118 protons, so there's still an insignificant portion of the, they make no true contribution to the mass, at least with normal methods of measurement and any reasonable person's degree of significant figures. So But that mass number is going to become important. So I need to tell you what was wrong with Dalton's postulates that, atoms of any given element are identical. And if you have a different atom, you have a different element. Or if you have a different element, it's made up of different atoms. Well, not all of the atoms of a given element are identical. We have these things called isotopes. They're atoms of the same element, but they have different masses. And they have different masses because they have different numbers of neutrons. They have the same number of protons. In fact, your atomic number, 1 through 118, equals the number of protons. Element number 1 has 1 proton. Element number 2 has 2 protons. Element number 3 has 3 protons. Element number 4 has 4 protons, and it really, truly is that simple. And for a neutral atom, it's also equal to the number of electrons. But if you look at carbon, there are 3 main isotopes of carbon. Carbon-12 is the most common form. 99% of all carbon is carbon-12. 1% is carbon-13, which has an extra neutron. Neutrons weigh 1, so you still have 6 protons. You must have 6 protons or you're not carbon anymore. These all have 6 protons. And in a neutral atom, they all have 6 electrons. So carbon has 6 protons and 6 electrons. Most of the carbon on Earth has 6 neutrons as well, but a small proportion, 1%, has 7 neutrons. And an even smaller, fleetingly small proportion has 8. And this carbon-14, with those 8 neutrons jammed into that nucleus with only 6 protons, makes it a little unstable. And this is a radioactive isotope. Carbon-14, we write it this way with its mass. We write it, when we're writing it, carbon-14. I guess you could write it out, but carbon-14. But when we're using our symbol, we write it carbon-14. Okay? They're all, element number 6. Okay? But with 6 protons. They have to be. If they don't have 6 protons, they're not carbon anymore. But they can have different number of neutrons. This carbon-14 is radioactive. It's an unstable radioactive isotope. Carbon-13, 1% of all the carbon you breathe, the CO2 in that breath, 1% of those atoms are carbon-13. But it's a stable isotope, and it substitutes, and there are very few isotopically discriminating reactions that discriminate between carbon-14 and carbon-13. It substitutes fine, carbon-12, and carbon-14 as well. But carbon-13 and carbon-12 react identically. They behave identically, except in a mass spectroscope, mass spectrometer, where they will be distinguished because they have different masses and would be accelerated differently based on their mass in a magnetic field. Anyway, isotopes are different forms of the same element with different numbers of neutrons, and that's the only thing that varies is the number of neutrons. But when you vary the number of neutrons, you vary the mass. So, if you look at a periodic table, you will see, for example, that I don't have one handy as I'm talking right now, but carbon is 12.011 atomic mass units, or Daltons, per atom. And that comes about from the fact that we take an average, a weighted average, just like you do in simple math, to calculate the average molecular weight, the average atomic mass, the average atomic weight of carbon, which is the average of all the carbon in the world. So we take 12 times 99% or 0.99, and we take and add that to 13 times 0.01 or 1%, and we get 12.012 or something like that. And that is a weighted average based on their relative frequency or relative abundances. And so when you look at the periodic table and you see atomic weight or atomic mass, it is the sum for all the isotopes of that element on Earth. Sometimes there may be two isotopes that are 50-50. Sometimes an element may only have a single form and single isotope. Other times there may be 5, 6, or 7 and more isotopes. It just depends on the element, and you need a chart of the nuclides to really tell that apart. And this is discussed in greater detail, as I said, in atomic chemistry, nuclear chemistry. I will say these isotopes have real-world uses in medicine because many of them are radioactive and can be used as tracers because we can detect radiation, or because radiation is frequently lethal, they can be used to kill. Hopefully, for example, kill cancer cells before you do the host. And because the radioactive elements decay at a constant rate, if you measure the amounts of the different isotopes of carbon, for example, once that person stops breathing and dies, that organism stops breathing and dies, it stops taking in isotopes of carbon and they begin to decay. And because they decay at a constant rate, the percentage remaining tells you the time since they stopped metabolizing and incorporating carbon. So they can be used as tracers, they can be used as radiation sources, and they can be used for dating. So there are practical applications to isotopes, and not every atom of a given element is identical in the sense that they can vary in the number of neutrons, and those are termed isotopes. Okay? Now, Gregor Mendel, and we're going to talk about the periodic table in greater detail in a later chapter where we talk about periodic trends, was a Russian chemistry teacher who invented the periodic table so that his students wouldn't have to memorize all the elements. And at the time, I think there are only 40 or 50 elements. This chart is incomplete, but it's been completed for a number of years now, so that dates your book. We have new elements and new names, and I'll post a news article about that to our class website. Anyway, if you list the elements in order of atomic number, in other words, in order of the number of protons, right? Oops, I can't make that bigger. You start to see a real order fall out where if you group the elements according to similar chemical properties, there is a periodic or repeating pattern in their properties that we now know is related to their atomic electronic structure. Now, the numbers in these boxes are all the atomic number, and we'll talk about this later. The atomic weight or atomic mass is almost also always shown in the periodic table. So the rows on the periodic table are called periods, and the columns are called groups or families. And elements in the same group have similar properties. And we're going to give some names to some of these. And I'll be using this terminology throughout the course. Now, one of the things I would like you to notice is that every periodic table has a stair-step line drawn through it. And everything to the left are metals. And everything to the right, and this is a brilliant name, over here in the light green, these are called nonmetals. And you can see there are a lot more metals than nonmetals. It's about 70-30, about 70% metals to 30% nonmetals. Metals, before I move on, and I'm jumping ahead a little bit, you know the properties of metals. They have three main properties. High luster, that means they're shiny. They conduct heat very well, and they conduct electricity very well. They're good conductors. And they, as we'll see, have high melting points. They're all solid except for one, and that's mercury over here. They're all solids at room temperature with high melting points, and what else? Good conductors of heat and electricity. Usually if you're one, you're the other. Not always, but usually. And high luster, high melting point. We'll leave it at that. I'll think of something else as we go along. And of course, the nonmetals over here tend to have much lower melting points. In fact, one of them's a liquid, that's bromine. And a number of them are gases: nitrogen, oxygen, fluorine, chlorine, or helium, neon, argon, krypton, xenon, radon are all gases at room temperature. One of them's a liquid. And they are very poor conductors of electricity, a variety of properties. None of them would be called shiny or lustrous. What else? Let's stop there. And then some are not good conductors. They're not bad conductors. They're semiconductors. And some of the ones along this line are termed the metalloids, and they kind of have properties of both. Now, not everything touching the line is a metalloid. For example, astatine, which has some semiconductor properties, is, based on its reactivity and properties, a halogen. Although it's very unstable, difficult to work with, it's radioactive, breaks down, and generates so much heat you can't get large enough quantities of it to study its properties. Polonium is clearly a metal, and aluminum is clearly a metal. So, but many of the ones touching the line are termed metalloids. They're neither metals nor nonmetals. They're kind of in between in their properties. So, as I said, when you arrange these elements in increasing atomic number, now Mendel did it by increasing atomic mass, which almost mirrors increase in atomic number, with a few notable exceptions. He saw that they fell into regular repeating groups or families with similar properties. For example, lithium, sodium, and potassium are very soft metals. You can cut them with a knife. They're all here in this first group, and they are extremely reactive. Uh, some of my students have seen what happens when you put sodium, for example, in water. Similar things happen with lithium and potassium. Really, all of those react with water to form a base or alkaline solution. And so we start giving some of these groups specific names. Group 1, and if I may say, the group 1A here, 2A, and then 3, 4, 5, 6, 7, and 8A, and I like to use Roman numerals with those, are termed the representative or group A elements. They're, I don't know, they act more straightforward. I think they're a little easier to learn. The ones between the two blocks of group A elements are the group B elements. It starts over here, 1B, 2B, 1B, 2B, go back to 3. We'll talk about that later too when we talk about electronic structures, but this group is called the transition metals. They transition between the two blocks of group A representative elements. And they have, when we start talking about ions, for example, multiple charges and get a little more confusing. But the group 1A are called the alkali metals because they form alkaline solutions. The group 2 metals do too, but they're not quite as reactive. They will still react and form an alkaline solution with water, and they're also common in the Earth's crust, so they're called the alkaline earth metals. A few people, chemists really only, refer to their group 6, oxygen, sulfur, selenium, tellurium, and polonium, as the chalcogens, but everyone calls the group 7 halogens. These are fluorine, chlorine, bromine, iodine, and astatine. And of course, group 8 are the noble gases. I don't know anyone who calls them the rare gases. They are arguably rare, but we've all heard of helium and neon, of course. So instead of saying group 1A, we sometimes refer to these groups by their names and call 1A the alkali metals, okay? Like I said, metals on the left, nonmetals on the right. Properties of the metals are high luster, good conductors, and high melting points. In other words, they all tend to be solid at room temperature. The nonmetals have lower melting points, and they tend to be poor conductors. And of course, the metalloids have properties that are sometimes like metals and sometimes like nonmetals. So they are in between, and that's where they're located in the periodic table. We will come back to the periodic table later. Now, let me see where we're at, because I wanted to go to a few more slides, and I will post an assignment to let you practice counting electrons and protons and calculating isotopic ratios. And don't worry, I will also be posting some videos, not just screencasts, of solutions to the problems, especially for these first few homework assignments. Now, chemical formulas, you know that you combine these atoms in different ways to make molecules, and if the atoms are different, compounds. Now, some atoms come together and form molecules diatomic molecules like hydrogen and oxygen, fluorine, chlorine, and bromine, all are what we call diatomic. But if we use different atoms, for example, not two hydrogens and not two oxygens, but two hydrogens and one oxygen, different atoms, we make a compound. And compound in chemistry has the same meaning as in English, for example, a compound sentence. And in math, you have compound means two different ones added together, okay? And there are ionic compounds, which we're going to talk about, and molecular compounds, which are usually put together with non-metals. You'll notice the hydrogen, oxygen, carbon are all non-metals if you look for their positions in the periodic table. Now let's talk about those diatomic models. I was taught very early that if it's in the periodic table and it ends in gen or ene, it's diatomic. Nitrogen, oxygen, hydrogen, fluorine, chlorine, bromine, and iodine are all diatomic molecules. So when we have chlorine, you will never find an individual chlorine atom in nature or an individual oxygen atom. When you take that breath, you're breathing in O2. Diatomic oxygen. Chlorine is present as Cl2. Hydrogen, H2. Nitrogen. 70% of our atmosphere is nitrogen. That is all present as N2. So, those are all diatomic molecules. Two or more atoms put together. Now, we need to talk about formulas when we put things together. And, if I can get to our list here. And so, the formulas, you just noticed I wrote, if I can get my pencil working, I wrote N2 for nitrogen, molecular nitrogen. And I wrote H2O for water. Those are chemical formulas that tell me the number and type of atoms present. The subscript tells me the number of atoms, and if it's a 1, it's understood. So I don't need to write H2O1. Okay, so let me get rid of this and end our discussion here. Before you go on to the next one, please stop and look at the assignment. Try to answer the questions, because those questions are models of the questions you're going to see on your test. Highly representative of the questions you're going to see on your test. So, until you do that, I will stop here, and we'll move on to the remainder of this short section remaining in the chapter for how we make and put together these compounds and how we represent them and name them. So that's where we're headed next, and I will talk to you on the next screencast for Chapter 2. Goodbye now.